Hello and welcome back to another video with It's Dr. Dan, and today we're going to be going through the tips and tricks on isomers, specifically constitutional isomers, which is when we have different branching patterns on the different alkanes, alkenes, alkynes, it's typically the different hydrocarbons. So these ones that we're going to specifically doing today is octane, which you might kind of realize is the more carbons you add, the more isomers you get. So we're going to show how to find all 18 isomers. I'm going to go through the exact steps on how to do this. So that way, if you're given a different structure like hexane or heptane or nonane or whatever, you know how to find all the different isomers that are possible. So now why is this something that's important is all because of intermolecular forces when we have all these different types of chemicals. So they give these things different properties, which is the whole reason why we even care about these isomers. Every single one of them is a little bit unique. They might all have the exact same chemical formula, but they all have different structures. Therefore, they're going to have slightly different properties that are going to be behind them. So you're going to see like their melting points and boiling points and things like that. They're going to adjust slightly with the different branching patterns they have because they can interact differently with each other. All right, so when you're doing your different isomers, first step is we always want to start with what the longest chain is. This is this is going to be your only straight chain isomer. Everything else is going to be completely going to be have branches. So when you're kind of doing this, you can do it in two ways. So let's say if we were doing expanded structures, which is usually where most organic students start, I usually, if I'm going to, let's say if I had to do it this way, I usually will write down like all my carbons first, right? And then I just want to like kind of number them, right? We can kind of see 1, 2, 3, 4, 5, 6, 7, 8. So I'm always kind of keeping a mental count for myself. Now, as we're going to be moving on, we're going to be kind of taking off like this last carbon here, and we're going to be moving it to different locations on this chain. Now, when it comes to isomers, though, the easiest way, though, is doing line structures. You can do expanded, we can fill in all the hydrogens, but you realize it's going to take a lot of time. So what I usually do is I'll just kind of draw the lines, right? So I got 1, 2, 3, 4, 5, 6, 7, and then 8, right? So that's going to be my base chain. And then from there, what we're going to use that as is like a template for ourselves. So this one is our first one out of the 18. So let's go to step 2 and see what we can do with that. So for step 2, we're going to be removing one carbon at a time, and we're going to be creating a methyl branch. So keep in mind, the most important thing for when you're doing these is keep count of your carbons when you're going through this. You need to have 8 the entire time. So it's really easy to do this and add an extra carbon here or there. So I'm going to copy and paste my octane from before, but I'm going to delete one of these carbons at the end. So right now I have a total of 7 carbons that we can see in our chain. So we have heptane is our longest. And what we're going to be doing is making a branch at the different positions. So for example, if I do this, right, I can put a branch, let's say at carbon number 2 as one of my choices. Now, is that the only option that you could have as an isomer? Well, let's just move it to different locations. We could move a branch at carbon number 3. We could also put a methyl branch also at carbon number 4 as well. All these are different possibilities that you have. Now, when you're going through this, you want to make sure that you're naming, right? So we have like 2-methylheptane, 3-methylheptane, and then the last one is 4-methylheptane. Now, you want to keep checking your numbering to make sure you're not doing any duplicates that can happen, because essentially we kind of think of like the 4-methylheptane as our last one. If I were to keep going and I put a branch at 5, that would have made a duplicate of number 3. So it's really easy to make doubles. So on here, right now, how many do we have? We now have 4 of the total 18 that are here. So let's keep going, and we're going to remove another carbon and continue. So as I was saying, you want to make sure you write down your names as you go. You don't want to have any type of duplicates or conformers as you're going through all these different structures. So conformers is just a fancy way of saying, hey, this structure's rotating. So it's very easy to kind of do that. What I mean is a lot of students will draw their structure. So let's say if I had 7 carbons, so a heptane, right? So I got 1, 2, 3, 4, 5, 6, and 7. You can never add a branch onto carbon number 1 or the last carbon. So like I'll commonly see, let's say someone adds a CH3 branch to the very beginning or something, but all it does is redefine your longest chain. So this is like a repeat of octane, right? Because it's still that 8 carbons long. So be careful when you're kind of doing that, so that way you don't accidentally make a duplicate and then you lose points on an assignment or a test just because you accidentally made a duplicate. It's super easy to do, but if you check your names, right, and check the longest chain every time, then you'll realize like, okay, we are avoiding any duplicates that can occur, right? So let's try to continue with trying to figure out the rest of these isomers. So as we're going to go through, what we're going to do is we're going to keep repeating step 2, which is where we make a new methyl group. So as you go and you make it shorter, you're going to have like 2 methyl groups moving around when you have like just a 6-member chain. And if you go lower to 5, you'll have like 3 methyl groups moving around. You might be able to try ethyls and propyls as a possibility for chains, but you just have to be careful that you keep naming and looking for the longest chain, because ethyls are possible with octane, but propyls will not be. You need to have at least 9 carbons for that to be a possibility when it comes to one of the isomers. So usually you have to have a very, very large molecule. So kind of like a little bit like of a rule of thumb here. So like when we did octane, right, we had 0 methyl groups. When we did heptane, which was our longest chain, we had 1 methyl group. When we have hexane as our base, we're going to have 2 methyl groups, and when we get to pentane, we'll have 3, and it'll keep going until you run out of room, right? So you got to keep in mind you have to have all those different all the carbons have to be present. So if I were to redraw this hexane, right? So now the whole idea is, all right, what are all the different possibilities for drawing these isomers? So like, for example, I could put, let's say, a methyl on 2 and 4, right? And that's a possibility that we could have here. So we could have 2,4 dimethyl hexane. And we could keep going with that, right? So we could put them, let's say, on 2 and 3 as an option. So we could do 2,3 dimethyl hexane. And what we're going to keep doing is we're going to keep repeating all the different possibilities here. So we could have, what else? We could have 2,2 dimethyl hexane. So we're just going to try to go through all of these possibilities, right? As we're kind of going through them. So just to kind of like fast forward for you guys, so you have to watch me like figure out like all the possibilities. Let's go through all the ones that are possible for having 2 branches. And if you want to pause here to see, can you figure it out? It's a good time to do that. So let's see if you get all the same number that is for 2 methyl groups moving around.
A few moments later.
Okay, so to fast forward, I started to write out all the names for this. So we had the first 2, right, which were 2,4 and 2,3. So from there, you essentially come up with every possible number combination you can think of. So I can get up to 10 of the isomers this way. So my next one would be 3,4. So we'll put a branch on the 3rd carbon on the 4th. Then we have another one where we have it on 2 and 5. You can double them up. So let's say if I put 2 of them on the same position, right? So they're like 2 little bunny ears kind of sitting on the structure, right? On one of these carbons. And then you could go to the next one, which would be 3,3. And you can kind of see like, okay, you can't go to 4,4 because then you're going to make a duplicate of this structure. So that's where it's going to end for this particular one. Now, is there any other type of carbon that is possible? You could potentially do ethyls as well. So how many ethyl possibilities are there, where you got to kind of play with like the different positions, because you got to make sure you're not redefining the longest chain. So typically it has to be like at least on carbon number 3 in order for an ethyl group to be possible, right? So if we kind of see on the very bottom here, I have it on the bottom, and it's not going to redefine what your longest chain is. So like we could have 3 ethyl hexane as one of our possibilities. And propyl wouldn't be possible when you get to 5 because it's going to make your longest chain something else. So these are all the different possibilities that we could have for just 2 branches. So what we're going to do is we're going to move to 5. So let's try to do pentane, and we're going to try to come up with the next, I think like 6 more that are possible for pentane. So for the first one, right, I drew a bunch of pentanes. So we're going to try to figure out all the possible combinations here. So now we're going to do 3 methyl groups moving to different locations. So like, let's say if I pick that first one here. So let's say if I just put a methyl group on, we'll do 2, 3, and 4, right? So if we were to do this one, we could see, okay, 2, 3, 4. and then it would be trimethyl, and being that 5 carbons is our longest, it would be pentane, right? So that'd be one option. And this is why I kind of like to line them all up like I'm doing here on the left-hand side of the page over here, right? Is because then you can overlap them and see like all the different combinations of branching that you can come up with. Like we could do, let's say we have 2 like little bunny ears on carbon 2, and then one of them on 3. You could do 2 little bunny ears on number 3, and then one of them on number 2, right? So kind of flipping those 2 structures. So you can see, okay, we have 2,2,3 trimethyl pentane. And you're going to try to come up with every single combination that you can think of for all these. Now, this is where it kind of gets tricky because it's a little easy to do some duplicates. So we can have like all these different 3 options, right? Now from there, well, all right, that's all the methyl possibilities. But don't forget, we had ethyl earlier. So what we could do is we could do, okay, let's do one methyl, and then let's say a ethyl. And then, all right, well, what's stopping us from, let's say, doing a methyl and an ethyl on the same carbon, right? As another possibility. And then the one that's missing is that we have 2 methyl groups on the first one, and then 1 methyl on the last one. I'm like trying to look through every combination. It's kind of hard to find them all sometimes, especially when you have this many. So, all right, so when it comes to naming them, right? So we do alphabetical when it comes to the branches. So we have 3 ethyl, 2 methyl, pentane, and then we'll have 3 ethyl, 3 methyl, pentane. And then our last one is 1 more trimethyl, which so it'd be 2, 2, 4 trimethyl pentane. Now, our last structure, right? So we have one more possibility is a what if we go one shorter? So what if we do a butane, right? So we have 4 carbons that are here. Can we possibly fit 4 more, 4 potential methyl groups on this structure? And the answer is yes, you can. We could do where we have, let's say, 2 methyl groups on carbon 2, and then let's say 2 methyl groups on carbon number 3, right? So we have all these little CH3s on all these structures. So how the hell do we do that? Well, we would do 2, 2, 3, 3 tetra methyl butane would be the structure. And that's how you can find all of them. So let's list them all out. So you have one stop shop for all the different structures. Go. So here is the complete list of all 18 isomers. So like if I were to be doing this on a homework, I would try to do exactly like what I did on the left side of this page, where I was attempting to like overlap all these so you can kind of see like, okay, we have 8, we have 7, we have 6, how long each branch is. And then we are each parent chain, and then we start moving our branches around in different locations to try to get all 18 of these. And hopefully you don't have to do this on a homework, but it's a pretty common one that I usually see on a lot of homeworks. I used to give it a lot to my students, but I kind of tamed it back a little bit. But sometimes I've even seen it on exams where you have to get like so many of these on maybe you have to get like 12 out of the 18 or something like that, just to show, hey, you know how to do isomers or, some kind of number like that. So I hope this video helped a little bit when it comes to how to draw the isomers, how to name a little bit, and just how to go through the general thought process of how to approach a problem of this magnitude. Okay, thank you so much for listening, and I hope you have a wonderful day, and I'll talk to you all later. Bye now.